Okay, so we were just talking about this brilliant and very thrilling example of the fly that's moving in a circle. So let's think about that fly moving in a circle again. But I want to think about the fly moving in the circle this time, not in Cartesian coordinates, but rather in polar coordinates. So how should we think about that? Well, maybe the first way to think about that is let's just think about what the position vector looks like in polar coordinates. Well, in polar coordinates, the distance of the fly remains 1. The distance to the fly from the origin remains 1 all the time, right? The fly is always the same distance from the origin. So if I were to sort of give the pair here of r comma theta, right? R is simply 1, right? And then theta, well, it takes 2 pi seconds for the fly to go all the way around. So in fact, theta is simply the time, right? Does that make sense? And I need to be a little bit careful here from a units perspective. Theta is in radians, time is in seconds, and so I actually need to do the time times 1 radian per second, so that I actually have radians in there from a units perspective. But it's 1 comma t. Let's think if that makes sense. Does it make sense? Yeah, at t equals 0, the fly is located here. At t is equal to pi over 2, the fly is located here. At t is equal to pi, the fly is here. Right? It does the same thing. And I'll observe at this point, look how simple this is. Right? For describing this motion in Cartesian coordinates, we have like cosine of t I hat plus sine of t j hat, right? Whereas in polar coordinates, it's just 1 comma t, right? This is just way simpler. And the reason it's simpler is because for this particular case, you've chosen a motion which is much more closely aligned with the polar coordinate system. So it's from a symmetry perspective, the motion is one that makes more sense to describe in polar coordinates. Okay, great. So you could also equivalently write this as r is equal to 1 in the r hat direction, right? Because that's what r hat tells you is where is the direction that you have to go in to get to r, and it's magnitude 1, which is a little confusing if you think about it for a second. So where did t go when I wrote r is equal to 1 r hat? Well, where t went is actually that r hat is a function. Let me do this, but where's t? R hat is a function of t. It's in here. Okay? In particular, if you think about what r hat looks like at time equals 0, at time equals 0, r hat is pointing over to the right, right? By the time you get to pi over time equal pi over 2, r hat is pointing up. R hat is pointing to the left by the time you get to t equal pi, right? So actually, even though this is an incredibly simple looking expression, it's just collapsed a whole bunch of information into r hat, right? Okay. Well, so what do we do with that? Well, let's see if we can take a derivative, right? Because that's what this is about, is how do we take derivatives in polar coordinates? Well, the velocity as a function of time is the time derivative of the position vector as a function of time, right? Which is d by dt of 1 times r hat. Well, product rule, d by dt of 1 is 0. d by dt of r hat is we're not sure, right? So we've got 1 times d by dt of r hat. So let's take a second to think about what d by dt of r hat is, and there are a number of ways to get at this. Personally, I think the easy way to get at this is just to go back to Cartesian coordinates for a minute to see what the answer is, and then it makes some sense as soon as you start to think about that. So we'll recall that r hat in Cartesian coordinates can be written as cosine of theta I hat plus sine of theta j hat, right? When theta is 0, r hat points in the I hat direction. When theta is pi over 2, r hat points in the j hat direction, so this is right, right? So if theta is a function of time, what's d by dt of r hat? Well, it's d by dt of cosine of theta of t times I hat plus sine of theta of t times j hat, right? And now all the powers of AP calculus come back. It's time to pull out our friend the chain rule, right? We've got a function of a function, and so d by dt of cosine of theta of t is going to be minus sine of theta of t, right, times d theta by dt times I hat, right? That's what I'll get when I do the chain rule for this first term. And the second term, simply I will get plus cosine of theta of t times d theta by dt times j hat, okay? Now, if we pull out the d theta by dt here in general, we get d theta by dt, which I'll actually write in the following convention. D theta by dt can also be written as theta dot, right? That's what d theta by dt is. So it's theta dot times minus sine of theta, I hat, plus cos of theta, j hat. And I'm just assuming now that theta is a function of time. That's actually implied by the fact that I've written theta hat here. Now, at this point, this is when there's like the, oh, wow, whoa, look at that. That's so cool. It's really hard for me to do this enthusiastically on video. But it is actually really cool because this should look really familiar. This here is what we called theta hat before, right? Theta hat points in the direction of increasing theta. When theta is 0, it points in the plus j hat direction. When theta is pi over 2, it points in the minus I hat direction. So in fact, dr hat by dt is theta dot times theta hat. And what do you think that d theta hat by dt is? Well, it's really tempting to say something like, oh, I bet it's r dot r hat. If you did that, you would be really wrong. And let's say that were the case, r dot times r hat. Why is that wrong? Well, one way to see that that's wrong is that the units don't work. Okay? Because if you look at the left-hand side, you've got d theta hat by dt. You have simply 1 over seconds, because theta hat is dimensionless. On the right-hand side, you have r dot, which is meters per second, times r hat, which is dimensionless. So you have meters per second is equal to inverse seconds. Doesn't work from a units perspective. So we probably have to actually think about things a little bit more. The other thing to think about is, in fact, if this were the case, this says that whenever r is changing, the direction of theta hat is changing. But in fact, if you're here and you just change r, you might move out to here. The direction of theta hat is actually the same at both of those points. So theta hat is not changing even though r is changing, right? What causes theta hat to change, is the same thing that causes r to change, right? When you change the value of theta, you change the value of r hat, right? So when I go from theta being here to theta being here, the direction of r hat changes and the direction of theta hat changes. So we actually expect that theta dot is going to show up here and not r dot. Let's actually do the math and check that that works. I'm already at 9 minutes on this, but we'll do it anyways. So d theta hat by dt is going to be equal to what? Well, it's d by dt of, let's write out theta hat, minus sine theta I hat, plus cos theta j hat. Take our derivatives. When I take my derivative here and use the chain rule, d by dt of sine theta is cosine theta with a negative sign still. And then I pick up a theta dot there. Here I pick up a negative cosine, or I pick up a negative sine theta times theta dot. So I'm going to get a theta dot times minus cos theta I hat minus sine theta j hat. In other words, I get minus theta dot times r hat. And I will stop at that point, and in the next video we'll maybe spend a little bit of time thinking about why this makes sense, because it's one of those things that often makes people's heads hurt a little bit.